Welcome back to the deep dive. Take a moment. Just look around you right now. Seriously. Chances are you're probably wearing something printed. Maybe a t-shirt, some athletic gear, could be a hoodie with a logo. Or perhaps you're looking at, I don't know, a branded mug or that, cool promo item you got somewhere. These things are just everywhere. They're woven into our daily lives, so common we barely even notice the details behind them. But lurking beneath that simple, bright graphic, there's this hidden challenge, a really persistent one. It's a challenge that's quietly plagued manufacturers and designers for decades. Even advanced tech struggles with it. We're talking about those moments, the ones when colors just bleed, or they mysteriously show up where they shouldn't. Sometimes it's subtle, sometimes it just ruins the whole look, turns a sharp design into, well, a blurry mess. It can spoil a whole batch of expensive sportswear or make that custom tee look, not so great. Today, we're not just like scratching the surface. We are diving deep into the fascinating but often frustrating world of controlling synthetic polyester dye sublimation and migration, specifically in textile screen printing. Now, I know those terms, sublimation, migration, they might sound a bit technical, you like dense science jargon. But trust me, by the end of this deep dive, you'll get it. You'll have a really clear understanding of the what, the why, and most importantly, the how of these tricky things. Our mission today, to unpack this whole intricate dance, between the dyes, the fabrics, the inks, and the heat. It's this performance that constantly gives screen printers headaches. We want to reveal the surprising science behind what just looks like a simple, annoying bleed.
You really have hit the nail on the head there. Persistent is absolutely the word. Ever since synthetic fabrics really became widespread in screen printing, printers have been wrestling with these problems. Dye sublimation, dye migration. It's baffling, really.
Yeah.
It almost feels counterintuitive, doesn't it? You'd think with all the amazing tech leaps we've seen, better dye stuffs, fancier dyeing techniques, even those special bleed-resistant inks, you'd think these issues would be gone by now. History. Yet, despite all that progress, better inks, better flash units, precise curing tech dye migration and sublimation are still a huge challenge, often a costly one for printers. And to really truly get to the bottom of it, to diagnose it properly and find solutions that actually work long term, you first have to understand every single part of this puzzle, all the components involved in this complex interaction. And like you said, this isn't just some abstract technical headache for the printers. It directly impacts the quality, the look, the feel, and the lifespan of the clothes you and I wear every day.
You're absolutely right. It's fundamental. So let's unpack this right now. Those terms dye sublimation, dye migration, they sound scientific, maybe a bit intimidating, but they describe very real, very annoying problems in printing. We really need to understand the distinct characteristics from the get-go because they involve different things happening, they look different, and logically they need different solutions, right? Targeted ones. So let's start with the first one, the disappearing act.
Indeed. Let's start with synthetic dye sublimation. Okay, so at its core, sublimation is this unique physical change. It's where something goes straight from being a solid to being a gas. It completely skips the liquid phase. You can picture it pretty easily. Think about ice cubes in your freezer. You know how sometimes they seem to shrink over time, but they never actually melt into a puddle. That's sublimation. They're turning directly into water vapor. Now, in fabrics, it's similar, just way more subtle. It's an interaction between the specific dyes used to color synthetic fibers and, crucially, heat. What's absolutely vital to get here is that most, maybe even all, synthetic dye stuffs will sublime. But, and this is key, it happens at a specific temperature, and here's where it gets nuanced. This isn't one magic number for all dyes, not at all. That exact temperature depends heavily on a few things that are all linked together. First, the specific type of synthetic dye used. Second, the exact dyeing processes used when the fabric was made and colored. And finally, it depends on the specific synthetic fibers in the fabric itself. So imagine these bright dye particles looking stable in the fabric. Then, under the wrong heat conditions, poof, they turn into an invisible gas, just like that shrinking ice cube. And that gas is ready to move around and potentially mess up your ink layer. That's sublimation in action. Printers really need to watch out for it.
Okay, so if sublimation is the dye doing a vanishing act, like Houdini, then dye migration is more like, I don't know, an oily intruder, something sneaking in. Yeah, the basic idea of migration is the movement of these dyes from the fabric into the ink that's printed on top. And then eventually, often sneakily, they start showing up on the surface of the print. It might look like a shadow or a faint version of the fabric color bleeding through, or maybe just dulling the ink colors like a slow creep. Now, how does this happen? It's not just random. It's a very specific chemical thing, almost unavoidable sometimes. It's an interaction between those petroleum-based polyester dyestuffs, the stuff giving the poly its color, and the petroleum-based plasticizer that's in standard plastisol inks. Think of it like this. That plasticizer, it's not just there to make the ink flexible. It acts like a solvent. Pretty powerful one. It basically dissolves or devolves any leftover polyester dyes, especially the ones just sitting on the fabric surface. Once those dyes are dissolved, they're not stuck anymore. They can travel. They literally migrate through the plasticizer network inside the ink film until they hit the surface. And boom, you see the bleed. It's almost like the ink is like thirsty for that dye. And here's where it gets really interesting. And yeah, a bit confusing maybe. This isn't just about heat. I mean, heat definitely plays a big part, as we'll get into. But fundamentally, it's about chemical compatibility. Like the ink's oil, the plasticizer, is naturally drawn to the fabric's dye oil and carries it through. It's a sticky situation, literally. And it means you can't just fix it by turning down the dryer, you know? You have to understand the chemistry behind it.
And that's exactly the challenge. They are distinct processes, different mechanisms at play. But it's really crucial to remember that even though they're different, these two often happen together. Or one can definitely make the other worse, especially when heat gets involved. For example, if some dyes do sublimate because of heat.
Right.
They turn into gas, enter the ink film, and then resolidify. Now they're basically residual within the ink, and then they become available for the plasticizer to pick up, which leads straight to migration. See, it's like a domino effect.
Ah, okay. One triggers the other potentially.
Exactly. And this whole thing brings up a really important question for us and for printers. What role does the fabric itself play in all this? Because as you'll see, it's not just sitting there passively, it's a huge active part of the equation.
Absolutely. The fabric isn't just a blank slate. It's a very active, sometimes temperamental player in this whole chemical drama. The specific type of synthetic fabric, the amount of polyester in it, it's incredibly influential. Polyester has all these great advantages, right? That's why it's so popular, why we see it everywhere. High-tech sportswear, comfy everyday shirts. But it's those exact advantages that kind of ironically can make these printing challenges even worse. Let's talk about the polyester advantage for a sec, because understanding why it's used helps us see the problems. First off, incredible shrinkage resistance.
Yeah.
Unlike cotton, which can shrink like crazy, maybe 5% or more.
Oh, yeah, easily.
Polyester holds its shape really well, wash after wash. That's huge for manufacturers. It means they don't have to overcut clothes to guess how much they'll shrink. Saves material, saves money. Second, polyester has amazing color strength and fastness. Colors stay bright, they don't fade easily in the sun or after tons of washing, especially compared to cotton. And third, it's relatively cheap to make. That keeps costs down for everyone, the maker and the buyer. So what does this all mean? Polyester's everywhere for good reasons, practical reasons. But because it's everywhere, printers just have to deal with its quirks, including this tendency for dye migration and sublimation. It's just part of printing on synthetics.
And you mentioned polyester content. That is absolutely key. It's a direct relationship, almost mathematical. The chance of polyester dye migration is directly proportional to how much polyester is in the fabric. Plain and simple. More polyester equals more potential for migration. You really can't overstate that. Now, garment makers, they know this. They are acutely aware of this issue. And it's really interesting to see how they're constantly innovating to try and fix it. We've seen a big shift in the market, especially with fleece. Manufacturers are offering more and more stuff with less polyester dye content. It's a direct response to the problem.
They're changing the recipes, basically.
Exactly. Instead of the old standard, that 50-50 cotton poly blend, which was, the workhorse for years but had its issues, now you can find garments with all sorts of different polyester percentages, each one trying to balance performance with printability. And for a lot of printers, one blend that's really emerged as a preferred option, kind of a sweet spot, is the 955 cotton polyester fleece.
95% cotton, just 5% poly.
Right. It gives you almost all the benefits of printing on 100% much fewer dye problems because of the cotton fibers, but you still keep that great polyester shrinkage resistance and durability from the 5%. It's a clever compromise. Works really well.
That makes sense. Best of both worlds.
It really is. And what's truly fascinating here, just showing the ingenuity in textiles, is how manufacturers are tweaking the actual fabric construction. Some have made amazing progress with advanced knitting techniques. It's pretty brilliant stuff. For instance, you can now find 50-50 blend fleece garments where, through really clever knitting, the cotton part of the fabric is deliberately put on the outside, the printing surface.
Oh, wow.
Yeah. And the polyester part is kept on the inside of the fabric, away from the ink. The beauty of a fabric like that is huge. The ink goes almost entirely onto the cotton. It's physically separated from the polyester. This design drastically cuts down the chance of migration because the ink barely touches the main source of the problem, those polyester dyes.
That's incredible. So the fabric itself becomes part of the solution.
Precisely. It's real-world problem-solving, built right into the garment structure. Shows you how much engineering can go into even seemingly simple fabrics.
That is a massive step forward, making the fabric proactive. But, okay, beyond the fabric itself and how much poly is in it, the actual dye used to color it and how that dye was applied back at the factory, those are also critical pieces, right?
Yeah.
So, okay, let's unpack that. There's obviously more to dye than just the color. It's about its chemistry, how it reacts to heat, how it reacts to ink.
Exactly right. Now, there are lots of different dye types used for synthetics, but for the t-shirt industry, for most of those 50/50 tees and fleece products, the main player is dispersed dyes. That's what's overwhelmingly used. These dyes are set into the polyester fibers under really strict conditions during manufacturing. Usually involves heating the fabric to around 70 Celsius, that's 160 Fahrenheit, often under pressure. This process makes the polyester fiber itself sort of swell up on a molecular level. That allows it to absorb the dyes, trap them deep inside.
Okay, so they're locked in there pretty good, usually.
Usually, yes. Once these dispersed dyes are properly set, embedded deep in the fiber, they are normally quite resistant to sublimating. They tend to hold fast up to about 182 Celsius or 360 Fahrenheit. And here is the aha moment for so many printers. The key insight that explains so much frustration. It's for this very reason that many still struggle with migration and sublimation, because they often, maybe accidentally, heat the fibers past that critical 182°C point during printing or curing.
They push it too far.
Exactly. When that temperature limit is broken, those dyes that were supposed to be locked in get released. They escape the fiber as a gas, and once that dye gas is floating around, it gets into the ink film that's just been printed. And once it's in the ink film, it can solidify again, becoming available for that migration process we talked about, ready for the plasticizer to grab it.
Wow. So this raises a huge question, doesn't it? Are printers unintentionally causing the problem themselves by overheating? Maybe just trying to speed things up?
It's a question every printer really needs to ask themselves. Are my processes accidentally exceeding these thresholds?
That's critical. A real process control issue. Now, dispersed dyes are the common ones, but you mentioned there's another type, cationic dyes.
Yes, cationic dye stuffs. These are really interesting for screen printers because fabrics colored with cationic dyes are generally very resistant to dye migration.
Okay, why is that?
Well, the mechanism is different. It's quite neat, chemically speaking. Cationic dyes need specially prepared fibers, usually polyester or acrylic. These fibers are engineered with specific guy sites, like little chemical parking spots, that allow the dyes to get locked into the fiber during the heat setting process. It forms a much stronger, more stable bond, makes them way less likely to escape or migrate.
Sounds ideal. What's the catch?
The catch is usually the cost. That specialized fiber prep and the different dyeing process mean cationic polyester or acrylic fabric generally costs more.
Right, makes sense.
But, for high-end products or jobs where you absolutely cannot have any bleed, that extra upfront cost could definitely be worth it for the quality assurance, the peace of mind.
Definitely something to consider for certain jobs.
And that brings us right back to the fabric dyeing itself. And critically, the rinsing process that happens back at the mill, these are absolutely paramount. From the fabric's perspective, there are two main things in the dyeing process that tell you how likely it is to migrate or sublime later on. First is just the sheer amount of dye used on the polyester fibers. During dyeing, the fabric gets heated up somewhere between 82 and 127 Celsius. That's about 180 to 260 Fahrenheit. This makes the dye sites in the polyester expand so they can soak up the dye. But here's the crucial detail. After the fibers are dyed, there can be residual dyes left just clinging to the surface of the fabric. They haven't properly bonded.
Like leftover paint.
Exactly like leftover paint. And it's precisely these surface dyes, these unbonded stragglers, that are super susceptible to migration. They're the easy targets for the ink's plasticizer later on.
Okay, so that's the first thing. How much dye in the leftovers? What's the second?
The second critical part is the rinsing process. This step, which often uses chemical washes and lots of water, is done specifically to wash away those residual dyes from the fabric surface. So here's the problem scenario. If a fabric got a lot of dye put on it and it didn't get a good enough rinse, maybe the process was rushed or not thorough enough. That fabric has a much higher chance of migrating later when it meets the ink and heat in the print shop.
That makes total sense. And does fabric weight play into this too?
It absolutely does. It compounds the issue. Think about a heavier fabric, like a thick 9-ounce 50/50 fleece, compared to a lighter 6-ounce 50/50 fleece. The heavier fabric, just plain, contains more polyester by weight, so it needs more dye to get the same color richness.
Right.
And because it needs more dye, it therefore needs a better, more thorough rinse during manufacturing to get rid of all those extra residual dyes.
Wow. So if the rinse isn't good enough on a heavy fleece...
You could have a real migration nightmare waiting to happen. And if we connect this to the bigger picture, it just highlights how important the whole supply chain is. Quality control, way back in the fabric mill, directly impacts the final print. A problem showing up in your shop today might have actually started weeks or months ago in a dye vat somewhere else entirely. The printer might have no idea.
That's a huge insight. It's so interconnected. Okay, so fabric choice, composition, its dyeing history, all vital pieces. But kind of underlying all of this, for both sublimation and migration, there's one big catalyst, right? Heat. Heat is absolutely central. It's almost like a character in this story. It drives the dye's behavior. It cures the ink. It's a powerful tool, but also, yeah, a huge risk factor, often underestimated. Here's where it gets really interesting and maybe a bit nail-biting. Understanding heat's exact role, all its nuances, is maybe the most critical thing for solving these problems. It's a real tightrope walk.
It truly is a delicate thermal dance, a very high-stakes balancing act. Now, the dyes in most commercial polyesters, they're heat set carefully so they have good color fastness for normal wear and tear. But the general rule is most of those polyester dyes used in t-shirts and fleece can handle temperatures up to a specific point, 182 degrees Celsius or 360 degrees Fahrenheit. The critical point, the moment everything changes, is at or beyond that temperature. That's when those polyester dyes start to sublime, turn into gas, and then aggressively push their way into the plastisol ink film.
360 Fahrenheit. That's the magic number, the danger number.
Pretty much. Now, here's a really important little nugget, a key distinction that can totally change how printers think about prevention. In most quality dyed fabrics, and quality is important there, it's actually the residual polyester dyes sitting on the surface of the fabric that sublime. It's not usually the dyes locked deep inside the fibers themselves.
Wait, really? So it's the loose stuff on top?
Primarily, yes, in well-made fabrics. This is hugely significant. It shifts the focus. Instead of trying to control dye deep in the fiber, which is mostly out of the printer's hands anyway, the main goal becomes managing those problematic surface dyes. It means that initial dye manufacturing, and especially that thorough rinsing process we just talked about, they are absolutely paramount. They prevent the problem before it even gets to the print shop.
Okay, that changes things.
For any printer, knowing this fact is invaluable. It helps you truly understand the specific reaction happening between those surface dyes and the intense heat you apply during flashing and curing. It explains why some fabrics seem like ticking time bombs, while others print beautifully.
And speaking of applying heat during printing, for screen printers, that flash unit often seems to be the main culprit, right? The biggest source of sublimation heat.
It very often is. Let me just say that again because it's so important. Most dye sublimation happens during the flashing process.
Okay, why specifically flashing?
Because during flashing, the fabric gets hit with incredibly intense direct heat. We're talking maybe 482 to 538 Celsius. That's a scorching 900 to 1,000 Fahrenheit radiating right off the flash unit panel.
Whoa, that's hot.
It is extremely hot, and the speed it happens is just astonishing, almost instant. Even though the shirt is only under the flash for maybe a few seconds, the polyester can hit that critical 182C sublimation point in mere seconds, maybe even less. It's because the flash panel is so incredibly hot and so close to the fabric.
So tiny time differences matter huge.
Hugely. We're talking microsecond differences. The gap between a perfect print and a bled-out mess could be as little as half a second under that flash.
Half a second. That's insane.
It's incredibly sensitive, and this harsh reality forces a crucial, often uncomfortable choice on printers. You have to prioritize careful heat management over just raw speed and productivity. Instead of blasting the ink and fabric with super high heat to make it flash faster, which is often the instinct, you should actively choose to print at slower speeds, maybe adjust your setup, and critically lower the flash unit temperature.
So it's a trade-off. Speed versus quality control. What stands out to you about that? It feels like it goes against the usual push for faster production.
What stands out is exactly that, the incredible precision needed. Like you said earlier, printers operate in this amazingly small thermal window. It is absolutely a tightrope walk. Very little room for error. On one side, most plastisol inks need at least 160 Celsius, 320 Fahrenheit, to cure properly, to be durable, washable. But on the other side, the polyester fibers have to stay below 182 Celsius, 360 Fahrenheit, to stop those residual dyes from sublimating.
Wow, that's only a 22C or 40F difference. That is tight.
It is incredibly tight. It means you have to be meticulous, really careful about the exact amount of heat and the exact duration of exposure for both the fabric and the ink. And that applies not just during that intense flash, but equally, maybe even more subtly, during the entire final cure in the main dryer. Every single degree, every fraction of a second counts inside that narrow, unforgiving window.
And given how incredibly tight that window is, the type of curing unit you use suddenly becomes massively important, doesn't it? It's not just about having a dryer. It's about having the right kind of dryer that gives you the precision you need.
Absolutely.
Forced air gas dryers, for instance. You mentioned they offer the most significant amount of heat control. Why is that?
They're engineered with sophisticated airflow systems. These systems can rapidly bring the ink film temperature up to that target, say 160 C. But the critical part is they can then plateau that temperature, hold it steady for a set period, creating a consistent thermal zone. This allows the ink to cure thoroughly and precisely without accidentally overshooting and overheating the fabric, which would trigger sublimation.
Okay, so they hit the target and hold it. What about the more conventional dryers, radiant heat?
Well, conventional radiant heat dryers, while common, often have limitations in this area. They tend to heat the ink much more slowly. Often the ink only just reaches that 160 C cure point right as the shirt is about to leave the dryer tunnel.
Cutting it close.
Very close. And their temperature plateaus, if they even have one, can be erratic. Many rely on less precise thermostats or just simple percentage timers. This makes it much harder to consistently maintain that ideal temperature throughout the entire ink film without potentially spiking too high.
So what this all means for you, the printer listening, the equipment you choose, your dryer tech, it massively impacts your ability to actually stay within that narrow thermal window. It directly affects your final product quality, consistency, and, yeah, most importantly, preventing that awful costly bleed. It's really an investment in quality control technology.
Couldn't agree more.
Okay, we've navigated the complexities of fabric, dyes, and that critical heat factor. Let's pivot now and focus on the ink itself. The ink isn't just, the color. It's a vital, active player in preventing these problems. It's your first line of defense, really. All right, let's unpack this then. How have ink manufacturers actually responded to this really complicated challenge? The whole sublimation and migration puzzle. What's actually in that bucket of ink?
Well, it's been this ongoing, really fascinating evolution, driven completely by what printers needed and the problems they were facing, as screen printing kept progressing, always pushing for higher quality, higher screen tension, thinner ink layers, softer feeling prints. Ink makers were basically tasked with making plastisols much, much better at resisting bleed, especially under these tougher conditions. If you look back historically, some early solutions used things like chemical bleaches in the ink formulation.
In the ink, wow.
Yeah. But today, partly because of stricter safety and environmental rules, like from OSHA and the EPA, and just a better understanding of the chemistry, many formulators have moved to safer, more advanced things like organic peroxides. These actually react chemically with stray dyes and kind of neutralize them. But it's not just about the act of blocking agents. Plastisol makers also strategically use special fillers. These aren't just for bulk. They do increase the ink's opacity, make it less see-through, which helps hide any minor bleed. But they also actively help the dye blockers prevent migration. They create another barrier, both physical and chemical, right inside the ink formula. It's a pretty sophisticated chemical cocktail, and it's always being tweaked.
There's a lot of complex chemistry going on there, stuff the end user never sees. But how well a specific ink actually stops dye migration seems to depend heavily on the type and the amount of that dye blocking agent used in that specific formula. It's not all created equal.
Not at all. Huge variations exist.
And here's a really critical point for you listening, and for any printer trying to guarantee quality. Unlike, say, the offset printing world, which has these super strict universal standards like swap inks, the textile printing industry doesn't really have universal standards for plastisol makers to adhere to.
That's a major challenge.
Why is that, though? Why no standards?
Well, partly it's because of the sheer variety of things plastisol has to print on. The substrates, the fabrics themselves. You've got everything from super stretchy athletic mesh to thick, heavy fleece, smooth cotton blends. Each one behaves differently. It's hard to make one standard ink work perfectly on everything.
Okay, that makes sense. So the consequence is.
Consequence is the responsibility falls squarely on the printer. It's up to you to meticulously figure out which specific ink product works best on the particular fabrics you print. It often means a hands-on process of trial and error, testing, which can be time-consuming, maybe frustrating.
Yeah, I can imagine. So the practical advice here seems pretty clear, maybe non-negotiable.
Absolutely. It pays off massively to print test random batches of your inks and your fabrics regularly because, as the experts always say, no two batches of plastisol are identical, and no two lots of polyester dyed fabric are the same. Things vary.
Wow, really? Batch-to-batch differences.
Definitely. So regular, diligent testing is essential. It's the only way to be sure the products you're using today will perform consistently and meet your quality standards tomorrow.
What's fascinating here is just how dynamic it all is, almost unpredictable. And the constant need for the printer to be vigilant, always testing. It's a continuous battle, but one you can win if you stay on top of it.
Exactly. And beyond the inks formula, the level of cure is absolutely fundamental in stopping dye migration. It's not just about hitting a certain number on your temperature gun. It's about the completeness of the chemical reaction happening inside the ink. Think of it like baking bread. You need the right temperature for the right amount of time for the inside to be fully cooked, not just the crust.
Good analogy. So how does that work with ink?
Okay, so at a molecular level, as the plastisol cures, the PVC resin, that's the main polymer structure in the ink, it actually swells when it gets hot. As it swells, it absorbs the liquid plasticizer, that oily part we keep mentioning, and that absorption process is what solidifies the ink film, makes it tough, flexible, washable.
Right, it locks everything together.
Precisely. Now, the migration connection becomes crystal clear if you think about what happens if the cure isn't complete, if it's undercured. If not all of the available plasticizer gets absorbed into that PVC resin during curing, then you have residual plasticizer left over. Still liquid, still floating around inside the ink film.
Ah, the leftover solvent.
Exactly. And this leftover plasticizer, being the chemical solvent it is, will aggressively dissolve or solvate any available dyes still hanging around on the fabric surface. Once those dyes are dissolved by the residual plasticizer, they're free to travel again. They migrate right through that network of unabsorbed plasticizer until they pop out on the surface of the ink.
And this is where the delayed reaction comes in.
This is exactly where it comes in. This migration process can happen anywhere from just 2 hours after printing all the way up to 6 weeks later.
6 weeks. Wow, that is sneaky.
It is incredibly sneaky. So a print might look absolutely perfect coming off the dryer, passes QC, looks great, but it could actually be a ticking time bomb ready to bleed out weeks later when your customer has it.
That's a nightmare scenario. So the solution
The
is...
solution is simple in concept, but needs diligence. For an ink that needs, say, 160C or 320F to cure properly, the entire thickness of that ink film has to reach and hold that temperature for the required time, not just the top surface, the whole depth, right down to the fabric. That's what properly locks up all the plasticizer and deters migration.
Got it. Core temperature, not just surface temp. And connecting this back, that delayed bleed, really highlights why proper curing and quality control are so vital long after the shirt leaves the dryer. It requires understanding the chemistry and being meticulous.
Absolutely critical.
Okay, so we have really broken down the what and the why.
Oh.
We've dived deep into the science of dyes, fabrics, inks, heat, all the players. But what does all this complex knowledge actually mean for someone doing the printing? For you, the printer, standing there at the press. We've diagnosed the problem. Now let's talk practical, actionable solutions. Let's build your playbook for success. Knowing that migration is mostly caused by that interaction, that dissolving action between the ink's plasticizer and those residual dyes on the fabric, the most logical, most effective solution seems to be minimize the contact between them, build a barrier, keep them apart as much as possible.
That's the core strategy, yes. Minimize the interface.
So one key technique for doing that is high-tension printing. Can you explain that a bit more?
Sure. So instead of pushing the ink deep into the fabric, which happens easily with loose, low-tension screens and too much squeegee pressure, basically driving the ink down into the fibers, high-tension printing lets you deposit the ink film precisely and cleanly on top of the fabric surface, like laying it gently on top.
Okay, and what are the benefits of doing that?
Several big ones immediately. First, the fabric doesn't act like an insulator blanket under the ink as much, so the heat from your flash or dryer can get to the ink faster and more efficiently. Means less time, maybe lower temps needed for a good cure. Second, you generally need less squeegee pressure. That's easier on your screens, saves wear and tear, helps keep your image sharp. And third, critically, it usually results in a thinner ink film, but one that's actually more opaque, sitting right on the surface.
Thinner and more opaque. How does that work?
Because it's not being driven down and spread out within the fabric fibers, it sits as a more concentrated layer on top. And that thinner film, because it's thinner, needs less time and lower temperatures during flashing and curing, which, as we've discussed, directly minimizes the chance of triggering that thermal dye sublimation. It's a whole cascade of positive effects.
That makes a lot of sense. It's about precision, not just brute force.
Exactly. And to really optimize this, printers should also look at using retentionable frames when printing on synthetics or blends. These frames maintain that consistent high tension much better over time, which really helps minimize that critical ink-fabric interface. Precision over penetration, as you said.
Precision over penetration. I like that. Okay, so high tension is one tool. What about controlling heat during flashing? You emphasized how critical that is.
Absolutely crucial. Let's reinforce that again. From the perspective of preventing dye sublimation during the print run, the golden rule, the absolute key, is to minimize the amount of heat the fabric and ink see during flashing. Now, I know many printers, maybe out of habit, maybe pushed for speed, might think, oh, my fabric doesn't get that hot during flashing, not up to 182C 360F, especially if they're just trying to quickly gel the ink surface.
Wait, just a quick flash.
But we need that reality check again. Remember the flash panel surface temp 900 on 1000 degrees F? And how close the fabric is. The time it takes for that polyester surface to hit the 182C sublimation point is incredibly short, scant seconds. We said it before, even half a second can be the difference between stable dye and sublimating dye. It is that precise, that fast.
So what's the actionable advice then, if you think sublimation might be part of your bleed problem?
If you suspect sublimation is contributing, it is absolutely worthwhile, even advantageous, to lower the heat setting on your flash unit and maybe even slightly shorten the flash time or adjust the press cycle time accordingly.
Even if it slows things down a tiny bit.
Even if it slows things down a tiny bit, what's truly fascinating and, yeah, sometimes frustrating for printers is just how much precision is needed here. How these seemingly tiny tweaks, half a second, a few degrees less heat, can make a massive difference in the final print quality. It really is a dance of millimeters and microseconds sometimes.
It sounds like it. And tying back to equipment one last time, it really reinforces the choice of curing unit, doesn't it?
It does.
The importance of that final cure and how different dryers give you different levels of control. You emphasized forced air gas dryers offering the best control.
Right, compared to conventional radiant heat. Specifically because they are designed with that airflow tech that brings the ink up to temp quickly, but then critically holds it there, maintains a stable plateau. That controlled environment is what prevents the fabric from getting accidentally overheated during the cure. It minimizes the risk of both sublimation and migration during that final, crucial step. It lets the ink cure fully without cooking the fabric underneath. It's about creating a controlled thermal zone, not just blasting it with raw heat.
Okay, wow. We've covered a ton of ground today on this deep dive. Really peeled back the layers on what just looks like a simple bleed. Let's try and bring it all together, because you, listening, you're now armed with some really powerful knowledge. You now understand the two distinct, though often linked, challenges. Dye sublimation, that gassy escape act, and dye migration, that sneaky, oily intrusion into the ink. You've learned about the surprising central role of polyester itself, how its makeup, its original dyeing, even its weight really matter. We've explored that delicate, critical balance of heat control, not just in the final cure, but maybe even more importantly, during that often underestimated flash stage. We've dug into the complex world of ink formulation, the blockers, the fillers, and why a complete cure right through the whole ink layer is totally non-negotiable for stopping bleed. And finally, we've given you specific practical printing techniques like high-tension printing and careful heat management that empower you, the printer, to tackle these issues, to turn potential problems into consistent quality results. The main message from our sources today seems really clear, and it's actually empowering. Synthetic dye sublimation and migration, they are manageable, they are controllable issues.
They are.
As long as you have a clear, precise understanding of how the dyes, the inks, and the heat are all interacting, you now have the insights to spot the potential for these problems before they happen, and you understand the safeguards, the procedures you need to address them effectively, turning frustration into mastery. And this really brings up an interesting question for you, our listener, just to think about as you go about your day. Considering all this intricate science we've discussed today, the specific dye type, the exact temperature, the timing down to half seconds, the ink chemistry, how the fabric was even knitted. Think about the next time you put on a printed shirt or hoodie, especially if it's a synthetic blend like polyester. that bright sports jersey, that sharp company logo on your fleece. Just pause for a second and consider how much unseen engineering, how much meticulous quality control at every single step, and how much precise thermal management went into making sure those bright colors stay exactly where they're supposed to, without bleeding, without migrating, without fading away. It's really a testament to how digging into seemingly simple things can uncover these fascinating layers of complexity. An often invisible world of craftsmanship, chemistry, and science right there on your back.
Absolutely. It definitely makes you look at that everyday printed tea in a whole new way. Much deeper respect for it. Well, thank you so much for joining us on this deep dive today. We hope you keep exploring your own curiosities because there's always more to learn. We'll catch you next time.